Hey everyone. So welcome to today's session. Today's session is about Hooke's law and elastic potential. It's an A-level physics session. And as always, we're going to split the session into two parts. And so we have two halves to the session. And at the end of each half, we'll do a couple of exam questions to check that we've been understanding what's going on. I believe that this will stay on the channel afterwards, so you should be able to see this later. But I can't confirm that for sure. But I'm pretty sure that it will stay on the channel. Yeah, good evening, everyone. Okay, cool. And well done, as always, for making it out on a Sunday. So I'll just mention a few things about how this works. So I am going to be going through, as I said, two bits of content. At the end of each one, we'll have some exam questions. Feel free, I'll be looking at the chat the whole time. So if you have any questions about what we're going through, just type them in the chat and I'll see them. And assuming I have time, I'll try and answer any of your questions. I also might have some questions for you as I go through, just to check you're kind of following along. So sometimes I'll ask you some questions and feel free to type the answers in the chat. Okay, so I think that's everything we need to get started. I'm just going to give it another 10, 20 seconds to let everyone come in. And as I said, today is Hooke's law and elastic potential. So it's all about extending or compressing things. And it's all about the energy required to extend or compress something. Okay, cool. Let's just go in and let's get started. So like I said, do just let me know if you have any questions. Okay, looking good. Oh, one sec. There we go. Okay, so just quickly about me, I am Matt. I'm the lead physics teacher here at SnapRevise. I'm a physics PhD student. And for a long time now, I've also been a physics tutor. Okay, good. So our objectives today are to understand two key terms associated with Hooke's law, which are the terms extension and compression. We're going to use Hooke's law to relate the extension or compression of an object to the force exerted on the object. So some relationship between extension and force. And we're going to define the elastic potential energy. That's the energy required to make an extension happen. And we're going to calculate it using Hooke's law and also using force extension graphs. So everything that we're going to do is going to rely on a few concepts that we're going to have in the back of our mind that we're only just going to review here to start with. So here's just some things to have in the back of your mind as we go through today's session. And there's two things that we need to kind of already know about, which are the basic physics of forces and the basic physics of, I guess, energy. Okay, so let's start with forces, and the laws for how to reason with forces are given by Newton's three laws. So I'll write in the first law. If anyone can write in the equation version of the second law, that would be great. It should, in fact, imply the law that I'm going to write. Okay, so Newton's first law says that if there is no force on an object, no force on an object, then it will stay at rest. If it was already at rest, it will stay at rest. Or more generally, whatever velocity it was at, it will stay at. So, or it will stay at a constant velocity. Constant velocity. Okay, looks like we're having a few issues with the pen. Just let me know if there's anything you can't read. Okay, then, so let's talk about the second law now. The second law is an equation. Yeah, perfect. The second law is F equals ma. F equals ma. Good. And this second law actually implies the first law. So why does it imply the first law? Well, let's imagine in this equation that the force was equal to 0. Then it would follow that the mass times the acceleration would have to be equal to zero. And that would imply that the acceleration is equal to zero. And the acceleration being zero is exactly what we mean when we say the velocity is constant. Because what is the acceleration? If you recall the definition of acceleration, it's the rate of change of velocity. So if the acceleration is zero, that means the rate of change of velocity is zero. In other words, the velocity is not changing. And that's what law one says. Okay, good. Now, the third one is a bit different, and it's usually said in quite a weird language. So usually it says for every action, there is an equal and opposite reaction. Now, action and reaction are not words that we've talked about so far, so we need to be careful about those. For every action, there is an equal opposite reaction force. So action is just fancy physics speak for force here. So in other words, they're telling us that whenever you see a force out there in nature, it always comes with an equal and opposite force. Forces always come in pairs, which are equal and opposite. Sum of all forces equal to zero. Is that a result of the second law? Yeah, so okay, that's a good point. I don't think I'm exactly answering the question, but there's something I didn't specify here, which is that this force here should be the sum of all forces. And another way of talking about that is to call it the resultant force. That's classic physics speak for the sum of all the forces. So it is the sum of all forces which is equal to ma. That is what the second law says. It's not something, the sum of all forces being zero or something, that requires extra stuff. The second law, I guess, says that when the velocity is not changing, the sum of all forces is zero. So if that's what you mean, then yeah, the answer is yes. But in general, the more general point is just in this equation, the F has to be the sum of all the forces on our object. So for instance, if our object is feeling a weight due to gravity, but it's falling through the air, so it's also feeling some air resistance. Maybe there's wind, which is pushing it off to the left. The F in F equals ma is the sum of all of these forces. It's this thing plus this thing plus this thing. Good, okay. So that's forces. And now we're going to go on to talk about energy. Now, one way to talk about energy is to talk about energy transferred. Another word for that is work done. So let's be very precise. Let's say I have a constant force acting on an object. Let's say, for instance, I push a block along a piece of floor. Let's say I pushed it this way. So it started over here in the dotted position. I moved it a distance s, and I moved it a distance s by applying a force V. I can calculate the energy required to do this, which is called the work done by the force, by simply, and I use the symbol W, by simply multiplying the force by the distance over which the force moved. And it's always the distance moved in the direction of the force. Now, okay, this is all very well, but this equation only makes sense if the force is constant while I'm pushing this block. What if I started off pushing the block really fast, really hard, and then later on, as I'm pushing at this distance s, I pushed less hard, but I still moved the block? Which of the many forces I applied at different times should I put in this equation? Well, I don't know how to choose. So if the force varies over time, for instance, if I pushed harder at the start and then less hard at the end, then we need something better than this equation. And instead, we use a graph. And in particular, can anyone say how I can get the work done, the energy transferred from a force against distance graph? So if the force was constant, I just multiply the force by the distance. But when the force is not constant, for instance, in this graph here, we can see that the force increased over time. Then I can calculate the work done by simply finding the area under the graph. This is a key idea. The work done, in other words, the energy transferred by the force, is equal to the area under the graph, where I'm saying that the work done in going from distance 0 to this distance, let's call it S, that would be this entire area here. There you go. Okay, good. And there are a couple of formulas for energies that it's going to be useful for us to keep in our head from the start. The first one is the formula for kinetic energy. So the idea is if I have some mass and it's moving at some velocity, as a result, it has some energy. And the energy that we assign to a mass m moving with velocity v is a half m v squared. And we call that the kinetic energy. You're absolutely right. If the graph is not given, you need to take the integral of f. So you just basically hope that you were lucky that the function, which is the force, that the force as a function of distance is some nice simple function that you know how to integrate. In general, it won't be. And so in general, even if you weren't given the graph and you're given the equation, you'd probably well, one thing you could do is plot the graph in the region you care about for that equation and then look at the area under it. And that's the same as approximating the integral anyway. Okay, good. We have one more formula here, which can actually be derived from this formula for work done. And this is gravitational potential energy. This is the energy that we have as a result of raising a mass some height delta h above the ground. Now, it makes sense that the amount of energy you have to put in to raise a mass would depend on how strong the gravitational field is, along with how big the mass is and the height you want to bring it up. So all in all, we get this formula, mg times delta h. So the energy that we assign to this mass being lifted by this height is mg delta h. Okay, good. So that's a kind of intro. That's going to be some of the stuff that's going to be good to have in the back of our head as we do the session. Just before we go on to the first half, here are the spec points we're going through for AQA and then OCR. And then also at Excel. Okay, good. So we're going to start by talking about Hooke's law. Now, not every object obeys Hooke's law, but Hooke's law is a law which is obeyed relatively often or to good approximations, so it turns out to be useful to talk about anyway. Okay, and Hooke's law is all about how much some object is going to extend when I exert a force on it. So if you imagine stretching a spring or some other material, to stretch it, you have to pull. You probably hold either end and then pull your hands apart like this. You have to exert a force to stretch something. You have to exert a force to cause an extension. And there's a nice equation that for some materials relates the amount of force you exert to the amount you'll manage to extend the object. Okay, and that's what Hooke's law is about. So we're first just going to lay down a couple of definitions. And these are the definitions of forces that stretch things and the forces that kind of compress things. And so you might guess, since we have the word compressive here, that tensile means to stress. So a tensile force is indeed defined to be a force which will cause an object to extend. In other words, it will cause its length to increase. Increase length. So a classic example would be me holding two ends of a spring and just pulling apart. That's a tensile force. And then there's compressive forces, which would be like me taking two ends of a spring and pushing in with my hands. So compressive force is one which will cause an object. I'm kind of going to go slightly in circles here. We're going to say it's the kind of force that causes an object to compress. And we're going to want another word for this because compress was also in the title, the thing we're defining. So in other words, it's the kind of force that will cause a decrease in length of an object. Okay, good. So let's take a look at a couple of examples. Let's imagine just a slightly different example to the one I was talking about already. Yeah, so Hooke's law, we haven't actually introduced it yet, but it's always going to relate force to extension. It doesn't have to be about a spring exactly, but yeah. Okay, good. So, what do I want to say here? Okay, so one way I can imagine exerting a compressive force is just taking my hand, and there's no way I'm going to draw a good hand here. Yep, there we go. I take my hand and I push up on this weight that's on this spring, sorry, to push it upwards. And as a result of pushing it upwards, I cause a compression. That's a compressive force. Okay, good. We could imagine the situation in which no force had been exerted. Or we can imagine, let's say we're just holding the mass there. Or we could imagine just taking our hand away and letting the mass pull on the string by its weight. Its weight is the mass times the gravitational field strength. And here, the mass which is hanging will exert a tensile force on the spring. Tensile force. Which stretches it, which causes its length to increase. So in each of these cases, compared to the length at which the spring would normally be, we'll call that x. We could talk about the change in length due to a compression, which we'll call delta x. It's like change in x. Or if it's tensile, we'll still give it the symbol delta x. This just represents a change in length. Okay, and then just one other definition before we do some more equations. We're going to need the definition of an elastic object. So I can imagine putting this mass on this spring, causing it to stretch, and then I could imagine taking the mass off, and the spring would probably pop up a bit again. But then one interesting question is, will the spring pop up to where it was originally, or will it stay always deformed slightly? Will it stay a bit longer than it always was? And the answer is it depends how heavy the mass I weighed on the spring was. But in general, we have the definition of the kind of objects that will return to its original shape once we stop stretching or compressing it. And that's what we call an elastic object. So an elastic object is an object which will return to its original shape. Shape. Once the tensile stretching, once the tensile or compressive force is kind of let go, in other words, is removed. So I stretch the spring and then I let go. Does it return back to its original shape afterwards? If it does, we call it elastic. Okay, good. So now we're ready to introduce the main equation that you're going to need to know to relate force that you exert to extension. And the good news is it's quite a simple equation. So the equation is called Hooke's law, and it states that, whoops, we lost a pen, and it states that the extension of a spring is proportional to the force which is applied to it. Now, there are other materials other than springs that would also obey Hooke's law, but certainly it's a law which is true of springs, which is applied. Good. And so let's just write this as maths. It's saying the force and extension are proportional. So it says this. Now, whenever you have a proportionality like this, you can introduce a constant to make this an equality. So one way of saying f is proportional x is to say that f equals k times the change in x for some k. And whatever this k is for our spring, we will call the spring constant. And it's essentially a measure of stiffness of the spring. Oh, we certainly spelled that wrong. Of the spring. I believe the higher the higher this number k, the higher the spring constant, essentially the stiffer the spring. Now we can figure out the units of the spring constant because the force is measured in newtons. The change in length, the extension, is measured in meters. So the spring constant, well, we can rearrange this to see that k is F over delta x. So the units of the spring constant will be, well, F is force, which is in newtons, over delta x, which is distance, measured in meters. So the spring constant is always measured in newtons per meter. Specifically, whenever we say that one quantity is proportional to the other quantity, that means that essentially you can introduce this number k. Yeah, so there could be other kinds of relationships between variables, but if the relation is that one is proportional to the other, then you can introduce a constant k. But there are other relationships you could think of. And those you would have to represent. Cool. Okay, but whenever you see proportional, that means you can introduce this number k. Sometimes you'll give it a different name, but that's okay. Okay, so let's look at an example. And the example we're going to look at is just an example of using Hooke's law. Okay, so it says calculate the spring constant k of a spring that extends by 0.2 meters when a force of 15 newtons is applied to it. Okay, well, if you're asked about the spring constant, then immediately you should remember that the definition of the spring constant is this. So we know straight away F equals kx, and we're probably going to have to use this formula to find this thing. Since we want to find the spring constant k, let's rearrange for k. And then let's hope that the question gave us these other two things. Otherwise, we'll have to think harder. And in this case, they did give us the force and the extension. The force was 15 newtons, and the extension due to that force was 0.2 meters. So that's 15, by the way, 0.2. Which is, in fact, going to be 75. And try to remember for yourself, what were the units of the spring constant? Well, we took a force, we divided it by a distance, so it's newtons per meter. Okay, good. Hopefully that's making sense. How are we feeling? We're feeling good, feeling kind of medium, feeling confused. Okay, well, we'll go ahead and have a go at some exam questions now. Okay, cool. And just let me know if you have any questions. So in this first question, we're told that we're given a spring, a meter rule, and a 100-gram mass. Describe how we would determine the force constant K of the spring. So we've got to design some kind of experiment. It's not going to be too long because there's only 3 marks available here. Let's just circle that. There's only 3 marks available. It's easier for me if I draw each of these bits of equipment. So we have a spring, okay. We have a meter rule, so that's something we can measure distances with, okay. And we have a 100-gram mass. Okay, we want to use these 3 things to determine the force constant K of the spring. So there's my spring. I want to know K. Okay, well, first of all, just to the side, let's do some working. We're being asked to determine the force constant. So let's remember the equation it appears in. It was F equals K delta X. So if you're being asked to determine the force constant, well, force constant, sorry, I should mention, by the way, the force constant is another word for spring constant. Sorry, I didn't mention that earlier. It's the same number, different name. Okay. So we see the force constant, or the spring constant, is the force divided by the change in length. So if we could figure out those 2 things, we could figure out the answer. So do we have a way of exerting a force on our spring? Well, certainly we do. We could hang our mass off of the spring, 100 grams. And is that going to give us some kind of extension? Yes, of course. We've exerted a force that causes an extension delta x. So we can figure out what force we've exerted. Here it's the weight, which is mg. So we have everything we need. So let's go ahead. Now we just need to take this idea and put it into something more structured. So first thing I'm going to do, if I want to calculate the change in length of this spring, I shouldn't just go ahead and put the mass on the spring because there's something I've forgotten there. I need to know the original length of the spring. So the first thing we're going to do is just measure it. And we can do that because we have a meter rule. So we should explain that we know that that's how we're going to do it. So the first thing we can do is measure and you can also call the original length the natural length. That's fine. So I'll just write that underneath. Original would be fine. Natural also comes up sometimes. So measure the original or natural length of the spring. And how are we going to do it? Well, they've told us we have this piece of equipment. So with the meter rule. Meter rule. Okay, good. Next, now we can hang the mass off the spring. Hang the mass off the spring. Okay, good. What next? Well, now we have a new length to measure. So we can measure new longer length. And subtract original length. Subtract original length. To find delta x. So the point is, let's call this x1, the original length, then we have x2, the final length. If we measure both of these, we can find the extension because it's just the difference between these two. Okay, just the measure mark. The force is the weight, which equals mg. And we actually know m is 100, but we'll come back to that. So k equals mg over delta x. And the final thing we should do is they actually told us this, so we should put this in. And we know g, so it's going to be 100 times 10 to the minus 3, because the standard units of mass are kilograms, times g, which is 9.81, and then divided by the extension, which we don't know yet. Okay, good. So that's how we're going to do that. I believe we have another question. Yes, we do. And it's a good one. Okay. In 7a here, we're told that atoms in a solid are held in position by electrical forces. Okay. These electrical forces can be represented by an imaginary interatomic spring between neighboring atoms. Now, this all probably feels like quite a lot of concepts, quite confusing, but let's just watch out for some of the key figures they've given us. Okay, so the interatomic spring obeys Hooke's law. Okay, that's good. Let's write down the fact that we know immediately. That means F equals K delta X. Good. And it has a force constant. Okay, that's the K. Just as a normal spring would have. So we can just pretend that this system is a spring. Okay. Researchers in America recently managed to determine the force experienced by an individual atom of cobalt when the atoms are squeezed together. The researchers found that a force of 210 piconewtons, that's a force, let's give it an F, changed the separation between a pair of atoms by a distance of so much. That's a change in length, that's got to be delta X. Okay, the first bit of the question asks us to state Hooke's law. We've already done that, so I'll go ahead and just write it down again. Hooke's law says the extension or compression of a spring is proportional to the force, this force could have been tensile or compressive, the force exerted on it. Good. Okay, and then we're asked to actually use Hooke's law. So calculate the force constant of the interatomic spring for a pair of cobalt atoms. And remember, we've been told it's okay to assume it obeys Hooke's law. So we know F equals K delta X. They told us that in the question by saying we can use Hooke's law. And the force constant is this number K. So let's rearrange for that. K is force over extension. What is the force here? It's 210 piconewtons. If you check your standard units, you'll recall that pico means times 10 to the minus 12. And we have the change in length, which is 0.16 nanometers. So 0.16 times 1 nano is times 10 to minus 9. If you chuck all that in a calculator, you'll get 1.312 newtons per meter. But they gave us everything to two significant figures. So we should give our answer to two significant figures as well, leaving us with 1.3 newtons per meter. I mean, an interesting thing to spot about this is how reasonable this number is. It's a very normal human number. It's just 1.3. It's not multiplied by some 10 to the power, some massive number, which is kind of crazy given it's this teeny tiny thing. It's just a pair of atoms connected together. Okay. So in the next part of this session, I believe we may have actually mistitled it here. One second. What we're going to be talking about is energy for springs, energy for objects which have been compressed or extended. So this Upthrust and Archimedes principle is a mistake. So you can just ignore that. So we're going to be talking about energy and Hooke's law now. That's what we're going to be talking about. So if you remember from our first kind of introductory slide, where we were remembering some useful things we want to keep in the back of our head, we had this idea that you can calculate energy or work done from a force by just doing force times distance. But if the force is not constant, then you had to find area under a graph. Okay. Now we're going to use that idea to calculate the energy stored in a spring when we stretch it. So let's imagine drawing a force extension graph for a spring. That means we draw a graph of force. Well, it shows the force required. Force required to attain a certain extension of an object, typically a spring of an object. So remember we had this law, force is directly proportional to change in x. In other words, F equals K delta X. This is a direct proportionality. You could draw this on a graph. And the point is that as delta X gets bigger, then this equation says F is also going to get bigger. And that's what we see in this graph here. We see that as delta X gets bigger, F gets bigger too. Good. Now, notice that this is basically what Hooke's law says. It says you have that if you drew force against extension, you'd get this nice diagonal straight line graph, because that's what a proportionality is. It's worth kind of pointing out that this is very reasonable law as well. It's basically saying that if I start with some spring, the more I want to stretch it by, the more force I'm going to have to exert. That's all this graph and this equation are really saying. Okay, now let's talk about the energy you have to put in to stretch a graph to a certain length, to stretch a spring to a certain length. So the work done in extending or compressing a spring is given by, well, it's just like work done for any force. It is the area under the force against distance. In this case, the distance is the extension. So it's the area under the force against, well, let's say the area under the force extension. That's what we called it before. Area under the force extension graph. Let's just get rid of that. Good. Okay, so we can see this on the graph. If this point here is my delta X and I want to know what the work done was, I can't just take F and the force and multiply it by the distance because the force was varying as I changed the distance. So instead, I have to calculate the area under the graph. And this height, if this height here is the force I finished on, then what I'm being asked to calculate is the area of this triangle. And this triangle has a height F and it has a base delta X. And the area of the triangle, in other words, the work done, should be a half times the base times the height. So it's a half F delta X. That's what we have here. So that's worth remembering. The energy due to extension of a spring is a half times the force you finish up at times the extension you finish up at. Now remember, since F is actually equal to K delta X itself, we can substitute that in and we'll get a half K delta X squared. So that's another formula that looks a bit more like the formula for kinetic energy. But instead of having velocity here, we have extension. So half K delta X squared. Okay, good. So that's the energy. What we've covered so far is the energy required, the energy transferred as we stretch a spring. And the other way of thinking about this is to say that what we're computing is the energy stored in a spring once it's been extended. And that energy will be released as soon as we let go. So that energy that would be released as soon as we let go, we call it the elastic potential energy. It's the stuff that gives it potential to do something when we let go, fling out of your hands. So we call it elastic potential energy, and it is defined to be the energy stored in an object when the object is extended or compressed. Extended or compressed. Good. Okay, and since the energy stored is just the energy we put in to change it to this new length, we can say the elastic potential energy is just the work done when we do the stretching, and we know how to calculate that. So the elastic potential energy in a spring, which has been extended by delta X, and which is being kept in position by a force F, is still just a half times the force times delta X. And also, if you don't know the force, but you know the spring constant, you can say the energy stored when you extend by delta X is a half K delta X squared. Maybe that's a more typical situation. Because you already know the material property of the spring, which is how stiff it is. You already know K. And you can read off the extension quite easily with a ruler. Okay, so let's have a go at a question. In this question, we're asked to calculate the elastic potential energy stored in a 15 Newton per meter spring when it is extended by 3 meters. So it's important to note that we haven't been told what this quantity is, but we have a hint from the units. Remember, spring constants are things that have units newtons per meter. So this here is the spring constant. And we know the extension they've given it here. Okay, so they want the elastic potential energy. Notice that they didn't give us the force. Nowhere in this question did they give us the force. So we don't want to use this equation here. It's going to be much easier to use this equation. So the elastic potential energy is a half times K, which is 50, times the extension squared, which is 3 squared. You can check that in a calculator and you should get 225 joules. Okay, good. So I believe, we have one more thing to say about elastic potential energy. And we're no longer going to be doing equations. This is just a kind of qualitative thing. That's a kind of situation where we have to describe or explain what's going on. And sometimes the examiner is going to ask you to explain or to describe the kinds of energies that were present at different points in a physical process. And they might ask you to figure out which kinds of energy were converted to other kinds of energy. Okay, so let's look at some concrete examples. Our first example is the example of flicking an elastic band. And definitely when you stretch an elastic band, going to flick it, you can see that you're putting elastic potential in it, energy in it. If you're to let go, all the energy that you put in by stretching it will be released and it will flick off your hand. So it certainly ends up with elastic potential energy. So let's describe all the energy transfers going on in the process of flicking an elastic band. So initially, the band gains elastic potential energy as it is back. Pulled back in the sense that we kind of just go to flick it here. Okay. Okay, and then we'd like to explain what energy we end up with. Well, when we flick an elastic band, the real goal is to end up with something that flings off your hand. In other words, you're looking for some mass to leave your hand with some velocity. You've made kinetic energy. You've made some kind of half v squared, where the elastic band has some mass and it's moving off at some velocity v. So this is transferred into kinetic energy. Kinetic energy when released, when the band is released. It's released. Okay, let's take a look at another example where we have to describe the energy transfers going on. Let's imagine the case where we begin by just holding our mass in place, for instance, again with my not so well drawn hand. And then at some point we let go of this thing. And as a result of letting go, it falls down because it's being pulled down by the weight. And as it's pulled down by the weight, that causes an extension. So that's going to cause us to have some elastic potential energy. We're going to stretch the spring. We're going to have made some elastic energy. We could get that elastic energy back if we took the mass off. Suddenly the spring would ping up and become kinetic energy. Okay, so let's describe this. So when at natural length, because that's where we're holding it here. So when at natural length, the mass here has gravitational potential energy because it could fall. It's been raised up. We're holding it there with our hand. We're letting it keep this gravitational potential energy. So the mass has gravitational, I may have spelled that right, gravitational potential energy. When we let go, this gravitational potential energy, which I'll abbreviate as GPE, is converted into elastic potential energy. Falls and stretches spring. Good. What was the formula again of gravitational potential energy? It was GPE equals mg delta h. You might notice it looks like a work done, basically, because it's the force you have to work against, the weight to lift something up, times by the distance you've raised it. Force times distance. But yeah, it's mg delta h. Okay, good. So how are we feeling? We have a couple of exam questions to finish off on. One of these is really good, actually. Well, actually, it's one long one, but I like the end of it. So yeah, how are we feeling? Just in case you still needed it, I'll draw it here. Gravitational potential energy was mg delta h. So far, so good. Okay, cool. Well, let's do some exam questions. As I said before, just stop me or let me know if you have any questions. Okay, so classic question. We already saw this as one of our exam questions in the first half. We get asked this a lot. We get asked to state Hooke's law. So Hooke's law says I should put the extension or compression of a spring is proportional to the force applied to it. Is proportional to the force applied to it. Okay, good, classic. Then we're asked to do some maths. So first of all, okay. Part B says a spring is compressed by applying a force. Figure 6.1 shows a variation of force with compression. We check the graph, we see force, we see compression. Alarm bells as soon as we're looking at this graph. This thing is in millimeters. We might need to watch out for that. That's not standard units. Okay, part 1 asks us to calculate the spring constant. Well, what is the spring constant? F equals K delta X. So K is F over delta X, and it doesn't matter which F or delta X we choose. Let's choose this one here to make our life easy. In this case, our force is 125, and our delta X is 50. But notice it's millimeters. Okay, so K is equal to 125 newtons divided by 50 millimeters. In other words, 50 times 10 to the power minus 3 meters. That's standard units now. Chuck that in a calculator and you will get 2,500 newtons per meter. Good. Part 2 was to show that the work done in compressing the spring by 48 millimeters is 2.9 joules. Okay, so let's find 48 on here. 48 is here, and that brings us to here, which brings us to this force here, and we see that these notches are each 5. So this is going to be 120 newtons. Okay. How do we calculate work done? Well, we have 2 formulas. Remember, it's this triangle again, so it's a half times base times height. Or more generally, you can just remember the formula, which says the work done is a half times the force times the extension. This is good. Now, notice we could have used a half K delta X squared. I've chosen not to do that because we just calculated K, and I don't want to make a mess in case I got K wrong earlier. I'm going to go back to basics and use F and delta X. What do we have? We have a half times, well, the force we agreed was 120. And the change in distance here was 48 millimeters. 48 times, as always, 10 to the minus 3 to make that into standard units. Chuck that in a calculator and you get a very pleasant looking number, 2.88 joules. They asked us to show that it's 2.9 joules, and that is correct because everything they gave us is 2 significant figures. So that is indeed 2.9 joules to 2 significant figures. Good. Now, the next slide that we're going to be looking at is following on from this question. So we're going to want to keep in our heads everything we learned here. So we're just going to recap it quickly. We stated Hooke's law. We know the spring constant now. This is just some spring that we're studying at the moment. And we found out the work done needed to compress this spring by a very specific amount, 48 millimeters. Now they're going to put this spring in context and ask us to figure out what's going to happen to this spring as it's used to fire something. Okay, so part C of the same question says figure 6.2 shows the spring in a toy gun. So it's the spring we were talking about before. The spring is used to fire a dart of mass 15 kilograms vertically. So here, this thing is 15 grams, and it's basically just some fancy, strangely shaped, strange looking mass. This is our spring from before that we just calculated some things about. We're told that the spring is compressed by 48 millimeters in the gun, and that's exactly the thing that we just calculated the work done required to do. The work done was equal to 2.88 joules. So we already know this. Okay. When the gun is fired, the strain energy, that's just another word for elastic potential energy, by the way. So let's write that in. The strain energy, the elastic potential energy, in the spring is converted into kinetic energy of the dart. Calculate the speed with which the dart initially leaves the spring when the gun is fired. Okay, so this is a great question. From just some properties that we know about conservation of energy, and from some of the things we learned about Hooke's law and energy today, we're going to be able to figure out essentially how fast this dart is going to leave this toy gun. Okay, so that's super useful. So how are we going to do it? Well, again, I kind of gave the game away. It's a conservation of energy. Sorry, second. So all of the elastic potential energy in the spring is converted into kinetic energy of the dart. So we know the final kinetic energy, which by the way is equal to half mv squared. We know that that is going to be equal to the initial elastic potential energy, which was this. We know it's going to be 2.88 joules. Okay, good. So we can use this to figure out the velocity because we know the mass. So let's rearrange. So we have a half mv squared equals 2.88. And we can rearrange and we'll see that v squared is equal to 2.88 times 2 divided by the mass. So our velocity is the square root of all of this. Okay, and what do we actually have here? Well, okay, 2.88 times 2. And then we have the mass. Okay, what was the mass? Oh yeah, 15 grams. And watch out, that is not standard units. Kilograms is standard units. So that's 15 times 10 to the minus 3 kilograms. Okay, chuck that in a calculator. You'll get around 19.5959, etc. But they gave us everything to two significant figures again. So we should give our answer to two significant figures. And what was it? It was a velocity. So it's 20 meters per second to two significant figures. Good, okay. And in the final part of this question, we're asked to give two reasons why the dart is unlikely to actually have 2.9 joules of gravitational potential energy when it reaches its maximum height. Okay, so what's the idea here? Well, they're saying originally we have the gun. And my drawing of the gun is much worse than theirs. There's our kind of thing that's being fired and the spring. And they're saying initially we have 2.9 joules here. We agree because it's been compressed by 48 millimeters. And eventually this dart is going to leave the gun. Everything's converted to kinetic energy. And then eventually it's going to reach its highest point. It's going to reach some highest point H. And so we could calculate the gravitational potential energy, which is mgh. And we would expect this to be 2.9 joules. And they're asking us to explain why it actually won't be 2.9 joules. So any ideas? Why are we not going to finish with this dart once it reaches its maximum height? Why is it not going to have all this initial 2.9 joules of energy in its height? Why is this unlikely? So any ideas? Good. So it is about air resistance, but because air resistance is a force, we want to kind of flesh that out a bit more to make it into an answer about energy. So when something feels air resistance, we can say that it loses energy to heat as it encounters air resistance. So the other thing I want to say is the kind of energy it loses due to brushing against all the air. But you're absolutely right. Good. So there's two answers here, and they're both pretty much the same. The one you mentioned was air resistance. Can anyone see where else we're going to lose energy in this gun? Something other than air resistance. Yeah, so for air resistance, the point is some energy is lost as heat due to air resistance. Good. So that's a really nice answer. Well done. What else? There's another answer. It's a very similar answer, but it's not about air. So air resistance, you essentially lose energy due to heat. That's another good answer, actually. So there are three good answers. You're right. Energy is lost to sound. You're absolutely correct. That's not the one I was asking for, but you're absolutely right. The other one I was going for is another heat loss. So some energy is lost as heat due to friction in spring. I guess that's one of the things you'll hear as well. So this friction as it rubs against the gun as it tries to release, as this dart rubs against the walls of the gun as it's released, that's going to lose heat. But you're actually absolutely right. It's going to cause sound loss as well. So you could have put sound here, or if you were being super good, you could have said some energy is lost as heat and sound due to the friction in the spring, or between the spring and the gun. Okay, good. So you should now be able to, that's the end of the session, essentially. You should now be able to understand the terms extension and compression. You should be able to use Hooke's law to relate extension and force. And you should be able to define the elastic potential energy and calculate it from Hooke's law and from force extension graphs. Remember, the elastic potential energy, it's the area under the graph, or it's a half K delta X squared, or it's a half F delta X. Okay, and that brings us to the end. So, does anybody have any questions? Anything I didn't answer? Anything people are still confused about? I might just mention by the end, while I'm keeping an eye on the chat for new questions, on this losing energy as heat thing. I guess you'd also lose energy due to sound from the air resistance. You know, you hear something. You can hear something when you throw it really fast through the air. So I could have said sound and energy for the air resistance. Some people might have worried that, like, aren't the air resistance and the friction the same thing? And this is kind of a technicality. They are two different things in physics. Air resistance is kind of the energy you lose due to contact or due to like moving through a fluid, which can be a gas or a liquid. Friction is about force stopping you moving due to contact with a surface, with a solid. So that's the difference. Friction is about contact with a solid, and air resistance is about moving through a fluid. And yeah, absolutely no worries. You also have a nice day. Were there any other questions? Okay, so I don't see anything else coming up. I'll just hang out here for another minute, just in case anything comes up. But for anyone who is here, thanks very much for coming to the session. I hope it was useful, and I look forward to seeing you at the next one. Okay, bye. And thanks to everyone who was typing in the chat as well. That was really handy. Okay, looks like there's nothing else. So, there is a question. How can you see from the graph if you have a constant force or not? Yeah, great question. Okay, I can answer this very quickly. If you have a force of force against distance, a constant force would mean a force that's not changing. That means whatever distance you choose, the force is the same. Whatever distance you look at, the force is the same. So if you plot force against distance, you get a flat straight line like this. This is a constant force. By the way, there's no danger here in always just calculating the area, because the area here, if this is a distance s and this is a height f, the area under this graph is literally force times distance, which is the formula for work done when we have a constant force. So you don't have to choose. If you've got a constant force, you know it, then you can use just work done equals force times distance. But if you're given a graph, you can always calculate the area. And if the force had been constant, you'll just get back the old equation. You'll just be doing it in a roundabout way. So it's completely safe from that point of view. Okay, good. So I think that is everything. So thanks very much, everyone, for coming again. And I will see you all at the next session. Okay, bye.